We've described kinematics problems using words. A car is traveling at 20 kilometers per hour for 3 hours. How far has it traveled? It's going a distance of 100 kilometers. It's going at 50 kilometers per hour. How long is it going to take? We know how to solve now those word problems involving speed and velocity. Now we want to represent them not using words, but using graphs. We want to graphically describe them. So what I want to do here right now, before we look at any graphs with numbers on them and where we have to do any kind of mathematical calculation, I want to just look at some shapes. Okay, you see 5 different shapes of position time graphs on the board. I want to identify what each of them represents. If I see this graph, it means the object in the graph, or the object represented by the graph, is doing this. Okay, first things first, this one. If you see a straight line on a position time graph, it means that the object, the car, the person, the animal, the whatever it is moving with a blank. 2 words. Constant speed. Technically, in this case, Ken, it would be constant velocity because it's position time, right? If it was distance time, it would be speed. Position time, technically, it's velocity. But in the end, if it's traveling at a constant velocity, it's traveling at a constant speed too. So we're going to say constant velocity. I'd probably mark it right, though, if you said constant speed. Here's a way to remember that. The line is constant. The line's not changing, right? If the line's not changing, it's constant, and what it represents has to be constant as well. It's constant. Oh, we've been talking about speed and velocity this whole time, so it's got to be constant. What did I say? I just told you that it should have been velocity, right? And then I went and wrote down speed. Constant velocity. Good. What about the next one? This one should be easier, right? It's a straight line, same as the last one was, but it's horizontal, it's flat. The object undergoing the motion described in the second graph is at rest. Look at, don't memorize this. Don't try to remember this from Science 10 or whatever. Look at it and say, what's happening here? The position isn't changing. If your position, Nick, isn't changing, then that means you're not moving. It means you are at rest. So you could say a velocity of 0, or you could say the object is stopped, or it's at rest, or it's not moving, or something to that effect. Third one. Still straight line. This one slopes downward. What does this one mean? Miles? Good. Constant negative velocity. I'll explain what that means in a second. Constant negative velocity. This does not mean that the car, or whatever, let's say a car, doesn't mean that the car is going backwards. It means the car is going in the backwards direction, the negative direction. If we define north as positive, and I drive to Calgary at a constant velocity, a constant speed, constant velocity, then that would be represented by the first graph. My position is increasing. My position is getting bigger as I go in the positive direction towards Calgary. What happens when I come back? My position relative to Okotoks is getting smaller. See what's happening here? Position keeps getting smaller and smaller and smaller. I'm not going backwards. I'm not driving from Calgary to Okotoks in reverse. I'm going forwards, but I'm going in the negative direction, the south direction, or the whatever direction that we represent as negative. Constant negative velocity. Constant backwards velocity. Not cars going backwards, but going in the backwards direction. Fourth one. Fourth one. First time we got a curved line here. Okay, what word do we take out of this equation here? What word should no longer be applicable? Constant. Constant was represented by a straight line. This isn't constant anymore. Okay, it's still velocity. So what do you have if you don't have a constant velocity? What kind of velocity do you have? Acceleration. It's an increasing velocity. Look, the line's getting steeper and steeper and steeper as you go. It's an increasing velocity, or you could say acceleration. The fifth one, here's the one that people always make a mistake on, get mixed up on. Fifth one. It's a curved line again, but it's a curving differently than the last one was. What's going on here? Deceleration. Good. Here's what a lot of people will say. It's going backwards, or it's going in the negative direction. It's not going in the negative direction. It's accelerating in the negative direction. It's still moving in the positive direction. Look, the position was 1. Now it's 2. Now it's 3. Now it's 4. Now it's 5. Now it's 6. The position keeps getting bigger. I'm still moving towards Calgary. But the position isn't changing as much as time goes by. So although I'm still moving in the positive direction, I'm decelerating. I'm slowing down as I still move in the positive direction. So you could say decreasing velocity. You could say deceleration. Or you could say negative acceleration. Would all mean the same thing. Now it's time for a little bit of what can we find from one of these graphs? Well, let me draw a little graph for you. On the x-axis, sorry, the y-axis is going to be position. On the x-axis is going to be time. Let's make the line look something like this. There's 4 things we're going to find here from this graph. There is position, there is displacement, there is average velocity, and there is what we call instantaneous velocity. I'll define that for you in just a moment, okay? Position, finding position. Well, the position is changing. So what you're going to want to do at any point is find the position at that point, at that moment in time. The position at this moment in time. The position at this moment in time. Easy. You know what you got to do? Go up and over. Look at the time here. Go up to the line, over. That's the position at that moment in time. What about at this moment in time? The position is different, right? Because you're moving at a constant velocity. Well, let's go up and let's go over. The position at that moment in time is that value right there. All you're going to do is go up and over. You're going to see a couple of different kinds of graphs here in the next couple of days. On any of them, whenever you want to find a value that has, as it's on its graph, the y-axis, you're just going to go up and over. You want to find a position, positions on the y-axis, go up and over. What about a displacement? What's displacement defined as? Change in position. So displacement is going to be the final position minus the initial position. So in other words, it's up and over times 2. Up and over, and then subtract. Subtract the 2 values of the up and overs that you got. Subtract the 2 values of the 2 positions that you got. So if I wanted to find the position here, up and over, here, up and over. If I want to find the displacement between this moment and this moment, I find this position, and then I simply subtract them. That's displacement. Easy enough, right? It's not that hard. It's just a matter of remembering what to do. That's all. That's the challenge, is just remembering it. Average velocity. Oh, you know this. The average velocity on a position time graph. I'm telling you, you know this. Even though you may have never seen this graph before. What's velocity? Mouse? You could say rise over run, absolutely. What's that otherwise known as? One word. Slope. Yeah, you can do that. I like to do this, though. I like to say the average velocity is the displacement over the time. Where'd you get the displacement from? Right here. So you see how one kind of flows into the next? Position is up and over. Displacement is, well, take your positions and then subtract them. Velocity is take your displacement and then divide it by time. So for number 2, we do something with number 1. For number 3, we do something with number 2. Right? They naturally flow in to the next one. Finally, number 3, finding instantaneous velocity on a position-time graph. Let me define that first. Instantaneous velocity is the velocity at an instant in time. The velocity now, at one specific moment in time. The velocity right here, or the velocity right here. How am I going to find it? I'll give you a hint. If it's a straight line, the velocity is constant, right? We said that a minute ago when we identified the shapes. So, if the velocity is constant, then the velocity at any instant is the same, isn't it? So if we find the velocity, the average velocity number 3, and it's constant, it doesn't matter at what point we want to find the velocity, it's the same velocity as the third one. If the average velocity between here and here is 6 meters per second, then the velocity right here is 6, the velocity right here is 6, and the velocity right here is 6, because it isn't changing. Velocity everywhere along that, it's got to be the same. Now, if it's not a straight line, things change. We'll deal with that later on. Okay, but if it's a straight line, then it's a constant velocity, it stays the same. Okay, let's take a look at the example on your worksheet, on the front side of your worksheet at least. We got a graph. Hey, this one's a straight line graph. We know it's a constant velocity, but we know it's a constant negative velocity, meaning it's moving in the opposite direction. It's not going backwards. The car's not in reverse. It's just going in the negative direction. It's coming back from Calgary as opposed to towards Calgary. What's the position of the object in the graph at time is equal to 10 seconds? Okay, what do you got to do for that? 3 words. Up and over. So let's go to 10. Let's go over here. Let's go 30 meters per second. Or sorry, 30 meters, I should say. Position 30 meters to the east. What's the displacement between 0 seconds and 10 seconds? Well, remember what displacement is. It's change in position. The position at 0 was 80 meters. At 10, it's 30 meters. Final minus initial is negative 50 meters. So far, so good? Okay, just get 2 positions, subtract them. Find the average velocity between 0 and 10 seconds. Now, Miles said we could take the slope of this graph. We can. We can absolutely take the slope of it to get the average velocity. But the same thing as the slope is displacement over time. The displacement we just found is 50. The time is 10 seconds. Negative 50 divided by 10 is negative 5 meters per second. What is the instantaneous velocity? The velocity at a specific moment, specifically this moment, at 2 seconds. How fast is it moving right here? Guys, it's not changing speed, right? If the average velocity is neg 5, and it's a straight line, then the velocity at 2 seconds is neg 5. What's the velocity at 7 seconds? Neg 5. Look, it isn't changing. It's a constant velocity. If it's on average negative 5 and it isn't changing, then it's got to be exactly negative 5 everywhere. You got that? Yeah. All right. You got a couple minutes to work on the back side of this worksheet now. See what you can do with that tonight and for the next couple minutes in class, and we'll take a look at it tomorrow, all right?